So let's look at a phase portrait in the neighborhood of an equilibrium. We have taken some time to change variables, look at capital X and capital Y that are our coordinates next to the equilibrium. We have rewritten our ODE system in capital X, capital Y as a linear system in which A, capital A, is the matrix we have introduced before of all the partial derivatives of f in the first line and partial derivative of g in the second line, both of them computed at the equilibrium point. We know that if we have a capital A being a 2 by 2 matrix, then we can rewrite it as a product of an invertible matrix P times a diagonal matrix. We have introduced a theorem stating that if the roots, the eigenvalues of A are different, then the matrix in the center is diagonal. So the green box that I have indicated is empty, doesn't have any value, is equal to 0. But in the case in which the roots are equal to each other, then we call this, it follows that in that little box there is a 1 instead. This is just a generalization of the case with two distinct roots, where we'll not be looking into it. If you want to look a bit more, you should know that this is called either a standard form or the Jordan form of the matrix. So once we have our linear ODE system, we have seen how this can be solved. We can solve it as an exponential of a matrix. If we can rewrite A as a product between P, the diagonal matrix, and P at the -1, then we can compute the exponential. And we can go through the steps as we did before. So writing the exponential matrix, applying the diagonalization, so taking out of the exponential P and P at the -1, and now the exponential of a diagonal is a diagonal of the exponential, so we can explicitly write the solution of our ODE system as a sum of two exponentials, both for x and for y. We're assuming here that the matrix we introduced before, capital A, has distinct roots. So our general solution for capital X and capital Y is, for X, a sum of e lambda 1t plus e lambda 2t with two constants in front, capital A1 and capital B1. And very similar for Y, except we change it to constant, where the constant depends on the capital A matrix that we introduce and on the initial values. If the general form has a 1 in the top right corner, then B is going to be A1 and A2 still will be multiplied by the exponential of lambda 1t, while B1 and B2 are going to be multiplied by the exponential of lambda 1t times t itself. Look how this is a generalization of the first order, by the way. So if we're able to write explicit solutions for capital X and capital Y as sums of two exponentials, then we can hope that the exponential is easy enough to understand the qualitative behavior of capital X and capital Y depending on lambda 1 and lambda 2. Qualitative means not exactly precise. Even though we do have a formula, what we're interested in is trying to have hands-on understanding of what X and Y are undergoing. So let's look at the very first case for this lambda 1s and lambda 2s. Let's look at a case in which they are different. So lambda 1 is different than lambda 2, but they are both purely imaginary. So lambda 1 is imaginary number times A, and lambda 2 is minus the imaginary number times A. pure imaginary eigenvalues. Then x and y are periodic, and you have an oscillatory motion around the equilibrium that we started with. We call this situation a center. What is the other case? Well, lambda 1 and lambda 2 are different. They are complex, but with a non-zero real part. So if you're looking at the exponential of lambda t, with lambda being complex, then you will have an exponential of the real part times the exponential of the imaginary part. The exponential of the imaginary part gives us oscillations, while the exponential of the real part could either, it's something that changes very fast, either it explodes when a is bigger than 0, so there is an exponential increase in time, while when a is smaller than 0, there is an exponential decrease in time. So you have to think about it as a combination of the oscillations given by the imaginary number and the exponential either increase or decrease depending on the sign of a. So we call these cases focuses. So we can have either an unstable focus that it starts at 0, 0 and it spirals away, the oscillations given by the imaginary number and the expansion given by the real part of it, or stable. That means it has a very similar situation, but instead of expanding, it's contracting. So it's spiraling towards our 0, 0 point. So stable focus. Stable and unstable comes really from a physical understanding of the situation. If you are at a stable fixed point, then any small change will not have any consequence in the long time, because you're just going to be cut back up towards the fixed point. While an unstable fixed point, it's true that its solution, if you are exactly at a fixed point, you're going to stay there forever. But if something happens and you're going to be kicked out, even by a tiny little bit, then you start getting away from it. Then the third case, lambda 1 and lambda 2 are real. This is usually this picture is the broadest case. Usually they are real and they have different signs. So lambda 1 and lambda 2 have different signs. I assume that lambda 1 is negative and lambda 2 is positive. So if in our phase space we draw the eigenvectors associated with lambda 1 and lambda 2, we know that if we are exactly at the eigenvector v1, then the only thing that is influencing the solution on this eigenvector is the value of the eigenvalue. The eigenvalue is negative, so what you're seeing is that the only behavior happening on this eigenvector is the exponential contraction associated with lambda 1 being negative. So if you are exactly on v1, you're going to 0. The opposite can be said when you are exactly on v2. When you are exactly on v2, then the only behavior on this eigenvector is the one associated with its eigenvalue being positive, so you have exponential increase away from the 0, 0 point. Then you can think of everything close to these eigenvectors, so not exactly equal to v1 or not exactly equal to v2, being something that is a combination of both. So if v1 is dragging you to 0, 0, if you're just off v1, you'll still be dragged to 0, 0 until you're close to v2, and then you're going to be kicked out, giving you this general understanding that things that are not exactly on the eigenvector are going to be dragged towards 0, 0, and then are going to be exploding away from it. Then the last option, lambda 1 and lambda 2 are different, but they have the same sign. Here I'm assuming that the sign is positive. So if you're exactly on v2, you're going towards 0, 0. If you're exactly on v1, you're going to 0, 0. But what happens outside of these of these options? Well, every other point is a combination of v1 and v2 with appropriate coefficients. And we have that one of the two eigenvalues associated to our eigenvectors is bigger than the other. So let's say lambda 1 is in absolute values bigger than lambda 2. So it drags the points faster than it does lambda 2. So if you are not exactly on the eigenvectors but somewhere else, the point first feels the very strong drag of lambda 1, and only when it is really close to the eigenvector associated to lambda 2, it starts feeling the other eigenvector. So you have this case in which lambda 1 crunches everything first, and then lambda 2 also combines things together. Last case, lambda 1 and lambda 2 are equal. So everything just behaves in exactly the same way, and it tends to our fixed point in the same way, doesn't matter where it is. Obviously, I'm looking at this case in which lambda 1 and lambda 2 are equal and negative, so everything is tending to the fixed point. But if they were lambda 1 and equals lambda 2 positive, then everything would be expanding from the fixed point in the same way. This is called a star, for obvious reasons. Remember that what we have built until now is based on the idea that capital X and capital Y are very small. So we are always really close to being at the equilibrium itself. If you want information far away from the equilibrium, then you need to draw the full phase space, and looking at derivatives of the vector field at the equilibrium will not give you enough information. But often, having information on how the equilibria are behaving gives you enough of an understanding of what is going on such that you can just try to patch this information together in an intuitive way that usually works quite nicely.